The previous examples where we were practicing the techniques of solving linear equations in 2 or 3 variables always resulted in one solution. That's not always the case, and what they want to point out here is graphs of 2 equations do not always intersect at one point, which means there's more than one possibility. For example, a system of linear equations could contain parallel lines or the same line. In these cases, the system of equations may have no solution or an infinitely many solutions. A consistent system has at least one solution. If there is exactly one solution, it is said to be an independent solution or system. If there are infinitely many solutions, then the system is dependent. And if there is no solution, then the system is inconsistent. So they're classifying it in 3 different ways. What we thought was just one simple idea has now turned into we've got to look at 3 different possibilities. Whenever we draw 2 lines on a piece of paper on the board, there's 3 things that could happen. We could draw 2 lines in such a way that they would intersect. We could draw 2 lines in such a way that one line lies completely on top of another, which is coinciding lines. And the third possibility when we draw 2 lines on a plane or on a piece of paper is that they would be parallel to each other. These are the 3 situations that we're going to tag some vocabulary to. If they have a solution, if they have some point of intersection, they're always going to be consistent. If they're consistent and they have one solution, then it's said to be consistent and independent. If they're consistent and they share an infinite number of solutions, then they're consistent and dependent. If there are no solutions in such a case of where the lines are parallel, then there will be no solutions or an inconsistent solution or system. Now, the best way to determine whether or not you're going to have a consistent, independent, dependent, or an inconsistent is to look at their slopes and their y-intercepts. So if you look at these in slope-intercept form, if we solve our equations for y, then we know that our slopes are different. Every time we have different slopes, the lines are guaranteed to intersect, and we're guaranteed one solution. In the case of the 2 lines that lie on top of each other, even though they may in appearances look different, if we write them in slope-intercept form, they reduce to exactly the same line. So even though we had 2 lines, we're going to draw 2 lines in the exact same location, same slope, same y-intercept, graphs are the same, there's an infinite number of solutions, so that means it's a consistent and dependent system. And the final case is when we looking at our equations in slope-intercept form, we can see that they have exactly the same slopes, but they have different y-intercepts. So if the slopes have to be the same or the same angle, and they have different y-intercepts, that's indicating that they're parallel, and therefore they don't intersect, and there's no solutions. So let's apply this to questions in A and B. In question A, we've got a negative 7x plus 3y equals 21, and a 7x minus 3y equals a 17. So what I want to do is I want to transform these equations into slope-intercept form. I want to put them in the y equals mx plus b. Because then I can examine their slope and their y-intercept. So in the first equation, I'm going to use and add 7x to both sides, so 7x plus 21. And then I'm going to divide by 3. I'm just going to label y sub 1, our first equation. So we have 7/3 x plus 7. Okay, so I got to keep that one in mind. Then I want to go back to the second equation, and I want to do the same thing with it. I want to solve this one for y. So I'm going to have 7x equals, I'm going to add the 3y plus 17. Then I'm going to subtract the 17, 7x minus 17 equals 3y. Then I'm going to divide by 3, so that means 7/3 x minus 17/3 equals y. And that's my second equation. Now I want to compare this equation to the first equation. So on examining these, our slopes are identical. So whenever we have identical slopes, then we've got 2 situations. They could either be coinciding lines where one lies on top of the other, or they could be parallel lines. So now we have to examine their y-intercept. Because the y-intercepts are different, we're going to have 2 different lines going in the same direction, so these are parallel lines. So every time we have parallel lines, we have a system that has no solutions, and whenever there have no solutions, they are called inconsistent systems. So this one is nothing more than an inconsistent system. A parallel with no intersection points is inconsistent. Now, if we look at our graph over here, I put that graph there so you can see what that inconsistent graph would look like. And letter B, we're again going to transform these into slope-intercept form. So in this first equation, I'm going to have 2y equals a negative 5x plus 12. Divide both sides by 2. Negative 5 halves x plus 6. That's equation 1. Second equation is going to be 8y equals a negative 20x plus 48. We divide both sides by 8. So I got negative 20 over 8x plus 48 divided by 8 is 6. Well, that 28 reduces, so that means our equation y sub 2 is going to be a negative. Divide top and bottom by 4 is 5 halves x plus 6. So now we'll look at our two resulting slope-intercept forms. They have identical slopes and they have identical y-intercepts, which means we have the exact same line. So if we were to graph them, they'd be one line on top of the other, as they're indicating here. And if you have two lines that lie on top of each other, we know that they are going to be labeled with this consistent and dependent classification. So our terminology is consistent. Consistent means there's at least one place where they touch, and dependent means they touch in every place. So consistent dependent means there's an infinite number of solutions. So a little terminology mixed in with transforming equations into the slope-intercept form. That's what that's about. Just a quick plug on another way of recognizing the consistent dependent solutions or systems. When you look at this equation and this equation, if you can quick get a little look on there, and if you multiply the top equation by 4, that 5 times 4, 5 times 2, and the 4 times 5, and 4 times 2, and the 4 times 12, if I transform that right away, it'll be 20x plus 8y equals 48, and that's identical to the second equation. That's another way that if you can see that one equation is nothing more than a multiple of another, that they are going to be the same line, so they're going to lie on top of each other, and it gives you another alternative to putting them in slope-intercept form.